Hello everyone, I'm Jyoti from BSc Chemistry Honors second year. This video is for visually impaired students, and the name of the chapter is Alcohols from Organic Chemistry, third semester. So let's start. Introduction. Alcohols may be recorded as hydroxy derivatives or aliphatic hydrocarbons depending upon whether the number of OH groups present in the molecule is 1, 2, 3 or many. Alcohols are further classified as monohydric, dihydric, trihydric or polyhydric respectively. It may be pointed out there that in dihydric, trihydric, and polyhydric alcohols, each OH group is attached to a different carbon atom. This is because the presence of two or more hydroxyl groups on the same carbon atom makes the molecule unstable and hence immediately loses a molecule of water to form an aldehyde, ketone, or the carboxylic acid. Monohydric alcohols. Alcohols containing one hydroxyl group per molecule are called monohydric alcohols. These can be divided into two broad categories, that is aliphatic alcohols and aromatic alcohols. First one is aliphatic alcohols. Alcohols in which the hydroxyl group is linked to an aliphatic carbon chain are called aliphatic alcohols. For example, methanol, ethanol, 2-propanol, etc. Aromatic alcohols. Alcohols in which the hydroxyl group is present in the side chain of an aromatic hydrocarbon are called aromatic alcohol. For example, phenyl methanol, 1 phenyl ethane 1-ol, 2 phenyl ethane 1-ol. Classification of monohydric alcohols. Monohydric alcohols are further classified as primary, secondary, and tertiary according as the OH group is attached to the primary, secondary, and tertiary carbon atoms respectively. For example, thus it is evident from both structures that the characteristic or functional group of primary, secondary, and tertiary alcohols are as CH2H for primary, CHOH for uh, CH2OH is greater than COHOH than CH2OH as the primary, secondary, tertiary alcohols structure are given above. Um, as in primary alcohol, the carbon atom is attached to another one carbon atom. In secondary alcohol, the carbon atom is attached to another two alkyl groups, and the in third tertiary alcohols the carbon atom is attached to three carbon atoms. uh, Nomenclature of monohydric alcohols. The general formula for monohydric alcohols is CnH2n plus 1OH where N equals to 1, 2, 3, etc. or ROH where R is the an alkyl group. Common system. In the common system, monohydric alcohols are called alkyl alcohols. Their names are derived by adding the word alcohol to the name of the alkyl group present in the molecule. Carbinol systems. In the system, methyl alcohol is called carbinol while all the other alcohols are named as derivatives of carbinol. For example, uh, ethanol would be called methyl carbinol and propanol would be called dimethyl carbinol. Iopec system. The system alcohols are called alkene. In the system alcohols are called alkenols. The name of an alcohol is derived by the replacing the final E from the name of the corresponding alkene by the suffix ol. The longest chain containing the OH group is selected as the parent chain and numbered in such a way that the carbon atom carrying the OH group gets the smallest number. The position of the substituents is then indicated by suitable numbers. OH group gets the smallest number. The position of the substituents is then indicated by suitable numbers. The common apex names of few monohydric alcohols are given below. Methods of formation. Alcohols can be easily prepared by the reduction of aldehydes, ketones, carboxylic acids, and their esters using a variety of reducing agents such as discussed below. Reduction of aldehydes and ketones. Aldehydes can reduce to primary alcohols and ketones to secondary alcohols either by catalytic hydrogenation, that is, addition of H2 in presence of a catalyst such as nickel, platinum, palladium, or or by reduction with complex metal hydrides like sodium borohydride and lithium aluminium hydride abbreviated. um, For example, here aldehyde can be converted into alcohol in the presence of hydrogen or nickel or nickel. The mechanism is given below. Reduction of alpha beta unsaturated aldehydes or ketones. Neither LiAlH4 or NaBH4 reduces isolated carbon-carbon double bonds. However, in case of alpha beta unsaturated aldehydes and ketones, LiAlH4 usually reduced only the carbonyl group, leaving the double bond intact. However, with NaBH4, the situation is somewhat different since aldehydes are more reactive than ketones. Therefore, in case of alpha beta unsaturated aldehydes, the reduction of aldehyde group occurs preferentially. However, with the ketones, a mixture of single reduction product, that is C double bond O, and the double reduction product, that is C double bond and C double bond C, is formed, in which the product single reduction usually predominates. Since LiAlH4 has a relatively stronger a tendency for reduction at the carbonyl group, therefore in the above case it gives 98% of cyclohexene-1-ol and 2% of cyclohexenol. Since LiHexenol since LiAlH4 is relatively stronger. In contrast, hydrogenation of C double bond C is much easier than that of C double bond O. Therefore, reduction of C double bond O cannot occur with reducing C double bond C double bond. In other words, catalytic hydrogenation reduces both the double bond and the carbonyl group simultaneously. To prepare exclusively an unsaturated alcohol from an alpha beta unsaturated aldehyde ketone, a chemoselective reagent such as and 9 is used. A selective reagent is that which attacks one of the several different functional groups. Because of the bulky organic group attached to boron adds to C double bond O much more readily than it's add to C double bond C. Thus, as Marvin Pondorf very rarely reduction. It is commonly used for the reduction ketones to secondary alcohols. The reaction is usually carried out by heating a ketone with aluminium isoperoxide in presence of isopropyl alcohol. Ketone is reduced to secondary alcohol at the expense of isopropyl alcohol, which is oxidized to acetone. Reduction of carboxylic acid. Carboxylic acid can be reduced to primary alcohols by LiAlH4. Because of the excellent sales it gives, LiAlH4 is widely used in a laboratory since it's somewhat expensive. Therefore, it can be used in industry only for the reduction of small amounts of valuable raw materials to be used in the synthesis of certain drugs and hormones. Mechanism like aldehydes and ketones, the reduction of carboxylic acids by LiAlH4 also occurs through nucleophilic attack by the hydride ion. The initial product of reduction is an alkoxide ion from which the alcohol is liberated by hydrolysis. Carboxylic acid can also be reduced to primary alcohols with diborane, that is B2H6. Reduction of esters. Esters can be reduced to alcohols by the following methods. Bovelt blank reduction. This method involves the reduction of esters to the alcohols with sodium. In refluxing alcohol, actually a mixture of two alcohols is obtained, one from acyl group and other from the alkoxy group, RCOOR. So here the we gave sodium in the presence of ethanol to the ester, then we will get an alcohol. The mechanism is given below. Reduction with LiAlH4. Ethers can be reduced with LiAlH4. Esters can be reduced with LiAlH4 to give a mixture of two alcohols, one from the acyl part and the other from alkoxy part. Uh, Catalytic hydrogenation. On commercial scale, carboxylic esters are reduced to alcohols by catalytic hydrogenation in presence of copper chromate used as a catalyst under high temperature and pressure to form alcohols. Physical properties of alcohols. Physical state. At ordinary temperature, lower alcohols are colorless liquids and distinct smell and burning taste. Thus, higher members are colorless, odorless, waxy liquids. Waxy solids. Hydrogen bonding. Since alcohols contain a hydrogen attached to the strongly electronegative oxygen atom, therefore extensive intermolecular H bonding occurs among alcohol molecules as a result. Alcohols exist as associated molecules rather than discrete monomeric molecules as shown below. Some important consequences of H bonding are discussed below. Boiling points. The boiling points of alcohols are much higher than hydrocarbons, alkyl halides, and the ethers of comparable molecular masses. The high boiling points of the alcohols can be easily explained on the basis of intermolecular H bonding existing between the molecules. Quite large amount of energy is needed to break these extensive hydrogen bonds which hold a large number of alcohol molecules together. As a result, their boiling points are much higher than hydrocarbons, ethers, or alkyl halides, which do not form H bonds amongst isomeric alcohols. The boiling point decreases with branching due to the corresponding decrease in surface area. That is, boiling point decrease in the order primary, secondary, and tertiary. Solubility. The lower alkyls are highly soluble in water, but the solubility decreases with the increase in molecular mass of the alcohol. The solubility of alcohol in water is due to the formation of hydrogen bond between alcohol and water molecules. The extent of solubility in any alcohol in water depends upon the capability of its molecule. In fact, hydrogen bonds with water. As the molecular mass increases, the hydrocarbon part, that is alkyl group, becomes larger, which resists the formation of hydrogen bonds with water molecules, and hence the solubility start decreasing. In other words, the solubility of alcohols in water decreases with lengthening of carbon chains. For example, the solubility of an alcohol decreases with the length of carbon chain increases. Amongst isomeric alcohols, the solubility increases the with branching. This is due to the reason that branching increases the surface area of the non-polar hydrocarbon part decreases, and hence the solubility increases. Chemical reactions of alcohols. The hydroxyl group is the functional group of alcohols. Therefore, most of the characteristic reactions alcohols are the reactions of OH group. In general, the chemical reactions of alcohols can be divided into the following categories: reaction involving the cleavage of COH bond, CO and H bond; reaction involving the cleavage of C and OH bond; reaction involving the alkyl and the hydroxyl group of the alcohol molecule; reaction involving the cleavage of O and H bond. The ease of cleavage OH bond of alcohols follows the sequence: primary alcohols, secondary alcohols, and tertiary alcohols. Reaction with reaction with active metals acidic nature. Alcohols react with active metals like sodium, potassium, magnesium, aluminium to form corresponding metal oxides with the evolution of hydrogen gas. This reaction suggests that alcohols are acidic in nature. The acidic character of alcohol is due to the reason that in alcohols hydrogen is attached to the highly electronegative oxygen atom, which withdraws the electrons of OH bond towards itself. As a result, OH bond becomes weak and ultimately splits off the proton. In other words, the acidic character of alcohol is due to the ability of the oxygen atom to accommodate the negative charge. However, alcohols are not weak acids, even weaker than water, as is evident from the following reaction. Here, stronger acid, that is H2O, displaces a weaker acid, that is ROH, from its salts and alkoxides. Um, Reason: this is due to the reason that the electron releasing inductive effect of the alkyl group increases the electron density around the oxygen atom. As a result, the electrons of the OH bonds are not sufficiently attracted towards the oxygen atom, and hence the release of the proton becomes difficult. In a nutshell, we can say that the electron releasing inductive effect of all alkyl groups makes the alcohols weaker acid than water. Comparison of acidic character of primary, secondary, and tertiary alcohols. As we move from primary through secondary to tertiary alcohols, the number of alkyl groups attached to the carbon having the OH group increases from 1 to 3. As a result, the electron releasing inductive effect would be maximum in tertiary alcohol and minimum in primary alcohols. In other words, primary alcohols are the strongest acids and tertiary are the weakest. Thus, the acidic strength alcohols follows as primary, secondary, and then tertiary. Reaction with Grignard reagents. Alcohols, being acidic, react with Grignard reagent which act as strong bases to form alkanes. However, be noted that the alkane formed corresponding to alkyl group of the Grignard reagent and the H atom attached to ON and S are called active hydrogen compounds. Alcohols, phenols, amines, thionyls, terminal alkynes containing active hydrogen on treatment with the Grignard reagent usually give a quantitative yield of hydrocarbon corresponding to the alkyl group of the Grignard reagent. This procedure is called derivative active hydrogen determination. The procedure is called Jarvitinov's active hydrogen of determination. Uh, knowing the volume of CH4 evolved at NTP, the number of active hydrogen atoms present in a compound can be determined. Thus, Jarvitinov's procedure is useful for determining the number of active hydrogen atoms in an organic compound. Reaction with carboxylic acid. Alcohols react with carboxylic acids in presence of few drops of S2SO4 or tri-HCl gas catalyst to form esters. This reaction, which is slow and reversible, is called esterification. When HCl gas is used as a catalyst, the reaction is usually referred to Fischer-Spear esterification. Isotopic transfer studies have confirmed that esterification involves cleavage of the OH bond of the alcohols. COH bond of acids is suggested by the mechanism. For example, when ordinary benzoic acid esterified with CH3OH, CH318OH2, the ester methyl benzoate formed was found to be enriched in it, while the water formed contained only the ordinary oxygen. Um, Relative reactivities of carboxylic acids and alcohols. The formation of tetrahedral intermediate during esterification is confirmed by the observation that the rate of esterification is sensitive to steric and hence the number of sites the substituents around the COOH group or the OH group in alcohols increases. The rate of esterification slows down. Reactivity with acidic chlorides or anhydrides. When alcohols are treated with acid chlorides, the atom of the OH group is replaced by the acyl group to form esters. This the reaction is called acylation if the acid halide and anhydride used over acetyl chloride and acetic anhydride uh, respectively. The reaction is usually termed as acetylation. However, if the benzoyl chloride is used, the reaction is called benzylation. When benzoyl chloride is treated with ethyl alcohol in the presence of NaH, ethyl benzoate produce the reaction of alcohols with benzoyl chloride and its derivatives in presence of aqueous NaOH is called Scotton-Bowman reaction. Uh, Reactions involving the cleavage of COH bonds. Reaction with halogen acids. Alcohols react with halogen acids to form haloalkanes. The order reactivity of halogen acid is HIHBr than HCl. This is due to the reason that I negative ion is better nucleophile than Br negative ion, which in turn is better than Cl negative ion. The order of reactivity of alcohol in these reactions is tertiary, secondary, primary. The order of reactivity can be easily explained on the basis of positive I effect of the alkyl groups, which tend to stabilize the incipient carbocation or the carbocation intermediate. Since the stability of the carbocation decreases in the order tertiary, secondary, primary, therefore the order of reactivity of alcohols are also decreases in the same order. With HCl, due to the low reactivity, the reaction of primary and secondary alcohols with HCl require the use of some Lewis acid catalysts such as anhydrous zinc chloride. However, no such catalyst is needed in the reaction of HCl with tertiary alcohols. Uh, when primary or secondary alcohol treated with alkyl halide, alkyl alcohol is treated with HCl in the presence of anhydrous ZnCl2, the alkyl halide is produced with reduction of water. This reaction of primary and secondary alcohols with HCl in presence of ZnCl2 is called Group's process. With HBr in this reaction, so also small amount of H2SO4 is added. Catalyst no catalyst is required for secondary and tertiary alcohols, which is uh, undergo dehydration in presence of concentrated H2SO4 to give alkenes. With HI, alkyl hydrates are formed. For example, methanol reacting with HI in the presence of reflux gives hydromethane. However, when an alcohol is heated with HI in presence of red phosphorus, hydrocarbon is produced. That is, when we treat methanol with 2HI in the presence of red phosphorus, we get methane. Role of anhydrous ZnCl2 in Grove's process. Anhydrous ZnCl2 being a Lewis acid accepts an electron pair from the oxygen atom of alcohol. The presence of positive charge on the oxygen atom weakens the RO bond and the ultimately breaks from carbocation shown in SN1 mechanism discussed above. If the structure of R negative such that it can undergo rearrangement to form a more stable carbocation, then the major product will be alkyl halide derived from the rearranged carbocation as discussed below. Uh, with reaction with thionyl chloride. Alcohols react with thionyl chloride preferably in presence of tertiary amine such as triethylamine pyridine to form alkyl chlorides. The reaction is called Dawkins procedure. Since SO2 and HCl both being gases escape into the atmosphere leaving behind almost pure alkyl halide, therefore SOCl2 method is preferred over phosphorus halide method for the conversion of alcohols into alkyl chlorides. Reaction involving both alkyl and hydroxyl groups. Dehydration of alcohols. By dehydration, we can remove a molecule of water. Alcohols on dehydration give alkenes. Like dehydration is carried out by heating a suitable alcohol with protonic acid concentrated H2SO4 or H3PO4. Lowest acids such as anhydrous zinc chloride or alumina can also be used. The actual temperature and the strength of the acid, however, depends upon the nature of alcohols used. For example, primary alcohols such as ethyl alcohol and propyl alcohol, etc., undergo dehydration when heated with 95% of H2SO4 at 443 to 453 K. Give the ethylene and propylene respectively. On the other hand, the dehydration of secondary and tertiary alcohols occurs with dilute H2SO4 at lower temperatures. Uh, in industry, thus the order of the dehydration of alcohol follows the sequence tertiary, then secondary, then primary. In industry, the dehydration of alcohol is carried out by the passing the vapors of an alcohol over heated alumina at 623 K. Then we will get alkenes. Reaction of alcohols with concentrated H2SO4 at different conditions uh, when on distillation under reduced pressure it gives diethyl sulfate. When heated with excess of ethyl alcohol at 413 K it gives diethyl ether. When heated with excess of H2SO4 at 443 K it gives ethylene. Mm. The step is slow and hence is the rate determining step of the reaction. Relative ease of dehydration of alcohols. Greater the stability of the carbocation, the more easily it would be formed and hence more readily the alcohol will dehydrate. Now the order of stability of carbocations follow the sequence tertiary, secondary and primary, hence the ease of dehydration also follows the same sequence. Tertiary alcohols and secondary alcohols and then primary alcohols. Rearrangement of carbocations, formation of an unexpected product. Uh, It has been observed that certain alcohols on dehydration produce such alkenes in predominant amounts in which the position of the double bond is not the expected from the structure of the original alcohol. The formation of such unexpected products can be easily explained in the terms of carbocation mechanism discussed above. We know that the carbocations always tends to rearrange to more stable carbocation shift. The structure permits either by 1,2 hydrate or 1,2 alkyl shift. Thus, in the dehydration of alcohols, if the initially formed carbocation is primary or secondary, and if the structure permits, it would always tend to rearrange to more stable secondary or tertiary carbocation before losing a proton. For example, in the above reaction, the initially formed carbocation is n-butyl carbocation, which being primary undergoes 1,2 hydrate shift to form more stable sec-butyl carbocation. Thus, it can be explained in terms of the rearrangement of the initially formed less stable carbocation to more stable carbocation, followed by loss of proton as shown above. Further, if the major product is also capable of showing cis isomerism, then it is always the thermodynamically more stable than trans product with the predominates, which predominates. For example, dehydration of 2-butanol gives 70% of trans 2-butene, 10% of cis 2-butene, and about 20% of 1-butene. Oxidation of alcohols involves the formation of carbon oxygen double bond with cleavage of OH CH bonds. These are also called dehydrogenation reactions. Since this involves loss of hydrogen from the alcohol molecules, the oxidation of alcohol can be carried with a variety of reagents such as neutral acid or alkaline KMnO4 K27 dilute HNO3. The ease of oxidation and nature of product, however, depends upon the type of alcohol used. Primary alcohols are easily oxidized first to aldehydes, then to acids, both containing the same number of carbon atoms as the original alcohol. Reagents such as calling reagent and chromium trioxide etc. are used. We can also use K2Cr27 with dilute H2SO4. Secondary alcohols are easily oxidized to ketones with the same number of carbon atoms. However, ketones resist further oxidation, but under drastic conditions, they are oxidized to carboxylic acids containing lesser number of carbon atoms than the original alcohol. Tertiary alcohols resistance to oxidation is neutral or alkaline KMnO4 solution, but are readily oxidized by oxidizing agents to a mixture of ketone and acid, each containing lesser number of carbon atoms than original alcohol. The oxidation presumably occurs alkenes dehydration of alcohols under acidic conditions. Uh, Action of hot copper. Different classes of alcohols give different products when their vapors are passed over heated copper at 573 K. Primary alcohol undergo dehydrogenation to give aldehydes. Secondary alcohol undergo dehydrogenation to give ketones. Tertiary alcohols undergo dehydrogenation to form alkenes in the presence of copper at 573 K. Distinction between primary, secondary, and tertiary alcohols. The three classes of alcohols can be distinguished from one another by following test. Oxidation. The three types of alcohol yield different products on oxidation explained on as explained below above. Action of hot copper. When vapors of alcohols are passed over hot copper, primary and secondary alcohols undergo dehydrogenation to give aldehydes and ketones respectively, while the tertiary alcohols undergo dehydration to give alkenes. Victor Meyer test can also be used, and the Lucas test. This test is based upon the reference and reactivity of primary, secondary, and tertiary alcohols with the hydrochloric acid. The test consists of treating an alcohol with Lucas reagent and equivalent solution of a mixture of concentrated HCl with anhydrous ZnCl2. The at room temperature, when turbidity due to the formation of insoluble alkyl chlorides is observed. If the turbidity abates immediately, thus alcohol is tertiary. If the turbidity appears in about 5 minutes, the alcohol is secondary. A primary alcohol, however, does not react with Lucas reagent at room temperature, hence no turbidity is formed. Interconversions of primary, secondary, and tertiary alcohols are given below. So now we will talk about the dihydric alcohols. Compounds containing two hydroxyl group attached to the different carbon atoms of their molecules are called dihydric alcohol. The general formula for dihydric alcohol is CH2NOH2 where N equals to 2, 3, 4, etc. Because of their sweet taste, they are commonly called glycols. Depending upon the relative positions of the two hydroxyl group, these are classified as alpha, beta, and gamma. So on glycols nomenclature uh, is given below. Now we will talk about the methods of the formation of vicinal glycols. By hydroxylation of alkenes. Vicinal glycols can be conventionally prepared by the hydroxylation of alkenes by the treatment of cold dilute aqueous alkaline solution of potassium permanganate, that is bare as a reagent, or treatment with osmium trioxide followed by hydrolysis with the aqueous solution. Here alkene, we can convert alkene into glycol in the presence of KMnO4H2, then or in the presence of osmium uh, in the tetroxide followed by the hydrolysis with aqueous solution of Na2SO3. Stereochemistry. Since both these reactions are cyclic, ester is formed as an intermediate. Therefore, both those reactions are syn hydroxylation process. That is, the two hydroxyl groups are added from the same side of the double bond to forces one to glycols. For examples, by hydrolysis of epoxides, acid or base catalyzed hydrolysis of epoxides, also called oxiranes, gives vicinal glycols. For example, ethylene epoxide presence of H2O gives ethylene glycol. Uh, the epoxide needed for the purpose of prepared of the action of acids such as perbenzoic acid, metachlorobenzoic acid, performic acid, acetone, alkene. Hydrolysis of vicinal dihaloalkenes. Vicinal glycols can also be prepared by hydrolysis of vicinal dihaloalkenes by aqueous Na2CO3 solution. By molecular reduction of carbonyl compound, ketones on reduction with magnesium in an inert solvent, benzene, ether, etc. Magnesium amalgam water give pinacols. This reaction may also be carried by photochemically. Reaction of 1,2-diketones with Grignard reagents. This method is generally used for prepared of higher vicinal dienols. Physical properties: state, odor, color, etc. Ethane 1,2-diol is colorless, viscous, liquid, and sweet in taste. Viscosity: because of the presence of two OH groups in the molecule, ethane 1,2-diol undergoes extensive intermolecular hydrogen bonding. As a result, ethane 1,2-diol molecule is highly associated and thus it has high viscosity. Solubility: because of the presence of OH groups, ethane 1,2-diol forms a hydrogen bond and water. As a result, ethane 1,2-diol is highly soluble in water. Further, being a polar compound, it's insoluble in non-polar and weakly polar solvent. Boiling point: due to the extensive intermolecular hydrogen bonding, the boiling point of ethane 1,2-diol is with high um, chemical reactions. The molecule of ethylene glycol contains two primary alcohol groups. Thus, its chemical reactions are essentially these of primary alcohol. Some important chemical reactions of vicinal glycols are discussed below. Reaction with active metals. Vicinal glycol react with active metals like Na, forming mono and disodium salts with liberation of H2 gas. It may be noted that two hydroxyl group react one after the other. When one OH group has completely reacted, the second starts reacting rather slowly. This is due to the reason that in glycol molecule, the negative effect of one OH group makes the other more acidic than which reacts the metal rapidly. However, when the OH group has completely reacted, the alkoxide formed exerts positive effect which makes the other OH group less acidic, and thus the second OH group reacts slowly. And it is because the reason that the second OH group needs more vargas conditions for the reaction to occur. Reaction with hydrogen halides. Vicinal glycols react with hydrogen halide instances to form dihaloalkanes. For example, here again the displacement of second OH group is more difficult than the first. This may be explained as follows. The reaction occurs via initial formation of the OH group to form the ozonium salt, which is subsequently displaced by nucleophilic attack by the chloride ion, either by SN1 or SN2 reaction. Once one OH group has been replaced by Cl, then the Cl atom thus introduced exerts its negative effect. As a result, electron density on the oxygen atom of the OH group decreases. This makes the protonation of second OH group rather difficult, and that is why the higher temperature is needed to replace the second OH group by Cl atom. Similar with HBr, first bromohydrin and then ethylene dibromide is formed. Reaction with phosphorus pentachloride, thionyl chloride, ethylene glycol reacts with PCl5 for thionyl chloride to form ethylene dichloride. Uh, Reaction with phosphorus trihalides, when reacted with PCl3 or PbR3, vicinal glycol give the corresponding dichlorides or dibromides. However, with Pi3P plus I2, the diode first formed being unstable decomposes to form an alkene and I2. For example, is given below. Reaction with nitric acid. with a mixture of concentrated HNO4 and H2SO4, ethylene dinitrate is formed. Reaction with monocarboxylic acid. On treatment with monocarboxylic acid, ethylene glycol forms monodiesters depending on the relative amounts of the reactants. For example, glycol diacetate is obtained when glycol is treated with glycol acid and in presence of small amount of concentrated H2SO4. Reaction with dicarboxylic acids. Uh, when the ethylene glycol is heated with dicarboxylic acid or there is esters, condensation polymers called polyesters are obtained. For example, condensation of ethylene glycol with tetraphthalate acid or methyl ester gives to trirelinodecaron. Reactions with aldehydes and ketones. When heated with aldehydes and ketones in presence of paratoluene sulfonic and acid catalyst, uh, ethylene glycol gives cyclic acetals and cyclic ketones. These acetals and ketones are widely used for protecting a carbonyl group in polyfunctional compounds where the reactions are desired at the other functional group in basic media. After the desired reaction, the carbonyl group is regenerated by hydrolysis of the acetal kettle with dilute mineral acids. Dehydration action of heat. Ethylene glycol when heated to 773 K gives ethylene oxide with concentrated H2SO4 when distilled with concentrated H2SO4. Ethylene glycol gives 1,4 dioxide which is used as industrial solvent with concentrated H3PO4 when heated with concentrated H3PO4. Ethylene glycol gives diethylene glycol which is widely used as industrial solvent. Oxidation of glycols gives a variety of different products depending upon the conditions of the reaction. The type of reagent used in the 1,2-glycol product may rises with or without the fusion of carbon-carbon bond. Oxidation in which the carbon-carbon bond remains intact. Oxidation of 1,2-glycol with usual oxidizing agents such as HNO3 gives a variety of products in which both alcoholic groups are oxidized but the carbon-carbon atom remain intact. For example, ethylene glycol on the oxidation with concentrated HNO3 mainly gives glycolic acid and oxalic acid. The other oxidation products such as glycoxylic acid are also formed in small quantities because they are more oxidized than readily oxidized than glycol itself. Oxidation involves fusion of carbon-carbon bond holding the hydroxyl group 1,2-glycols on oxidation with an aqueous solution of periodic acid or tetraacetate in an organic solvent undergo fusion of the carbon-carbon bond leading to the formation of aldehydes, ketones or both depending upon the structure of glycols. The oxidation of 1,2-glycols with periodic acid to give carbonyl compounds is sometimes called a Maillard reaction. Uh, Oxidation with lead tetraacetate. Similarly, lead tetraacetate first reacts uh, with the 1,2-glycol to form 5-membered cyclic acid intermediate, which subsequently decomposes to form the corresponding carbonyl compounds. Uses of Maillard reaction. The oxidation of 1,2-glycols with HIO4 takes place in quantitative yield by determining the quantity of HIO4 used and the nature of amounts of products formed. It is possible to determine the structure of polyhydroxy compounds. As discussed below, structure of determination, let us consider the oxidative cleavage of the three isomeric butanediols, that is 1,2-butanediol, 2,3-butanediol, 1,3-butanediol by HIO4. Determination of number of H groups present in an adjacent carbon atoms in polyhydroxy compounds. In case of simple polyhydroxy compounds, for every 2 adjacent hydroxyl group, 1 mole of HIO4 is used. Therefore, if there an adjacent hydroxyl group, moles HIO4 would be used. Thus, by knowing the number of moles of HIO4, use the number of adjacent hydroxyl groups in the molecule can be determined. For example, oxidation of 1 mole of glycerol, use 2 moles of HIO4 per mole of glycerol. Therefore, it contains 3 OH groups. Pinacol rearrangement. Substituted vicinal diols are referred to pinacols. Thus, when 2,3-dimethyl 2,3-butanediol is heated with concentrated H2SO4, it undergoes dehydration with molecular rearrangement to form Dutch beta methyl ketone, which is called pinacolon, and this rearrangement is called pinacolon rearrangement. Trihydric alcohols. As the name suggests, trihydric alcohols are compounds which contain three hydroxyl groups attached to the different atoms in the apex system. They are known as triols. For example, CH2OH, CHOH, CH2OH, propane 1,2,3, triol, glycerol, propane 1,2,3, triol. Methods of formation: by saponification of oils and fats. Glycerol is mainly obtained by the hydrolysis of oils and fats with caustic soda uh, from propylene on a commercial scale. Glycerol is also prepared from propylene. Propylene needed to for the purposes obtained by cracking of petroleum. It may be noted there at high temperature. Propylene reacts with chlorine to give a substitution rather than addition product. The reason being the under conditions of high temperature, the addition reaction is reversible, but the substitution reaction is irreversible. Synthesis from its elements. Glycerol can be synthesized from its elements. Physical properties: glycerol is colorless, viscous, and hygroscopic liquid with sweet taste. It boils at 563 K with some decomposition. It is miscible with water and alcohol in all properties. Viscosity: because of the presence of 3OH group, glycerol undergoes extensive intermolecular H bonding. As a result, the glycerol molecules are highly associated, and thus glycerol has a high viscosity, even higher than ethylene glycol, which has 2OH groups per molecule. Solubility: because of the presence of 3OH groups, glycerol forms hydrogen bonds with water. As a result, like ethylene glycol, glycerol also highly soluble in water. Further, being a polar compound, it is insoluble in non-polar and weakly soluble solvents like carbon tetrachloride, chloroform, etc. Boiling points: due to extensive intermolecular hydrogen bonding, the boiling point of glycerol is quite high, at higher than the of ethylene glycol. Some chemical reactions are given below. Reaction with sodium metal: some readily sodium readily reacts with primary alcoholic group at room temperature and less readily with the secondary primary alcohol group at 373 K. With evaluation of H2 gas, the secondary alcoholic group is not attacked at all. Reaction with halogen acids with hydrogen chloride, glycerol and tri-HCl 1 ratio 1 reacted 383 K to form mixture of alpha beta glycerol monochlorohydrins. However, on passing more HCl gas at 383, glycerol gives a mixture of alpha dichlorohydrin, alpha beta dichlorohydrin, etc. with hydrogen bromide. Like HCl, hydrogen bromide gives similar reactions with hydrogen, and different products are obtained under different conditions. When glycerol is treated with small amount of HI or Phe3, allyl iodide is formed. When large amount of HI used, main product is isopropyl iodide, which is believed to form action HI on allyl iodide according to the following reactions. Reaction with concentrated nitric acid and sulfuric acid nitration. When glycerol is added to form mixture of concentrated H2SO4 and HNO3, glycerol trinitrate is formed. Reaction with KHSO4 dehydration: we heated the anhydrous potassium, hydrogen sulfate, and hydrogen chloride or concentrated H2SO4. Glycerol undergoes dehydration to form an alpha beta unsaturated aldehyde. With dilute HNO3, a mixture of glyceric acid and tetranic acid is produced. With concentrated HNO3, a main glyceric acid is produced. With bismuth nitrate, only mesoxalic acid is formed. Uh, with periodic HIO4 acid with periodic acid, glycerol undergoes oxidative cleavage to form formaldehyde and formic acid. During the oxidation, periodic acid itself it is reduced to iodic acid with acidified potassium permanganate. When heated with acidified KMnO4 solution, glycerol gets oxidized to oxalic acid, carbon dioxide, and water. Reaction with phosphorus halides: all the three OH groups of glycerol react when with the treated PCl5 or PCl3 to form 1,2,3 trichloropropane. Reaction with monocarboxylic acid: glycerol reacts with monocarboxylic acid to form monodi and dry esters depending upon the amount of acid used and the temperature of the reaction. In excess of the acid and high temperature favor the formation of dry esters. For example, the acetic acid, glycerol, monoacetate, diacetate, and triacetate may be formed. Acetylation: when treated with acetyl chloride, glycerol forms glycerol triacetate. Reaction with oxalic acid at 1 and 10 degrees Celsius. When oxalic acid is heated with glycerol at 383 K, it forms glycerol monoxalate, which loses a molecule of CO2 to give glycerol monoformate. The latter then undergoes hydrolysis to yield forming acid at 230 degrees Celsius. Oxalic acid reacts with glycerol to form glycerol dioxalate, which loses two molecules of carbon dioxide to give alcohol. Uses in the preparation of nitroglycerin used on making dynamite. A mixture of glycerol trinitrate and the glycerol dinitrate absorbed on a kind of porous earth is called dynamite. Uh, Dynamite was discovered by Alfred Nobel, in whose memory the Nobel Prizes have been instituted. Dynamite is not only used for making bombs but also for making tunnels for the blasting of rocks. Nitroglycerin is also used for treatment of engine factories. As an antifreeze in automobile radiators, it lowers the freezing point of water and thus does not allow it to freeze in cold water. In medicines like cough syrups, lotions, etc., in the production of little or alkyl resin, a cross-linked polyester obtained by condensation polymerization of glycerol and phthalic acid, which is used in the manufacture of paints and lacquers. Thanks for watching.